So I guess we can start. So it's a pleasure to have here, aka remotely, Eric Steinbring. Most of the people here at Gemini know him because it's meeting us every Wednesday as a part of the Canadian NGO. But the history of Eric doesn't start with Gemini, but when goes a while ago to the University of Winnipeg when he had his bachelor thesis, University of Alberta when he had the master, and then he moved to University of Victoria where he got his PhD. He made me aware that I didn't know that in the 1999 is actually joined a project to make computer simulation of work on some imaging simulation of part of Altair. So it's being, without knowing, it was being part of the family of Gemini well before actually became NGO. And after a postgraduate study in in Santa Cruz in California, he moved back to Canada and is now part of the National Research Council of Canada. And today we'll make actually pretty interesting topics about how we can use our astronomical data a little outside proper astronomical observation, but trace global extinction and climate changes to sort of climate change with GMOS north and south data. So the stage is yours.
Well, thank you very much. That's a very kind introduction, starting from the University of Winnipeg. So my background is adaptive optics. I came to it through physics and math, in working on adaptive optics, as we know, you really need to understand the atmosphere. You need to understand changes in turbulence and orography of sites over a long time, and so to understand how adaptive optics systems work, what you really need to do is site testing. So much of my career has been working on site testing. So looking at sites over a long time to understand how they can intercompare, and also how changes at the sites affect, in terms of elevation above the ground and changes in orography, how that's affected. So I've also done site testing, not just on Mauna Kea, and in Chile for TMT, but also to really remote places like the high Arctic, doing site testing on the highest, most northerly mountains in the world. And you don't want to do that because you want to be in a cold, dry place, and with a stable atmosphere, and get away from the effects that you see at mid-latitude sites. So that's, we're always looking for better places and trying to find places that are stable and the best. So what's this talk about? So global extinction, and I picked this title on purpose. It's a pun, obviously. This is a discussion of changes in astronomical sky conditions over time. And global extinction, you might imagine, well, this is the end of the world. But to photometrists, a small change, incremental loss in throughput, in transmission of the atmosphere over a long time is important, and we should be looking for it. And it happens to be a portentous day to talk about maybe a auspicious day. Today's Groundhog Day. So asking the question, what's in our future for photometry and spectroscopy in terms of the quality of our photometry, the accuracy of our 0 points over time. So that's really a question about transmission of the atmosphere. So that's what I'm going to talk about. Can you see if my cursor, you can see my cursor in the screen, yes?
Yes, we can.
Okay, thank you. So I'm going to use that to kind of point out some things. So what is this talk not about? Well, this is not a talk about the end. These guys know what's coming. I really like this image. So of course, this is an image of the end of the Jurassic period, with the large asteroid going to impact the Earth. and kill off all the dinosaurs. If you look at these guys, I mean, they seem to know the end is nigh. They're looking up. They're asking the question, what's going to happen, and they seem to know the answer. So they look scared. So this is not this is kind of like I'm saying, the sky is falling, and I'm hopefully I say it tongue in cheek, but it is kind of like for photometry, this is kind of like a sky is falling, right? This is I'm going to look at changes in transmission of the atmosphere, but it's not as dire and not as serious as this. But we should, like them, look out. So, and in as this is Groundhog Day, as those animals were asking the question, what's in the store for us? Today, I don't know if people maybe in Hawaii you kind of know, if others are calling in from other places. This is really an East Coast of the U.S. Type thing. That this is some kind of a historical thing. Maybe comes from Europe. That if you're not familiar with it, on this day a groundhog is supposed to come out of its burrow, and if it sees its shadow, it must be sunny, I guess, and it'll go back into its burrow. And if it's cloudy, he doesn't see his shadow, and I think that's supposed to mean that that winter is almost over. So I presume that if there is any logic in this, that if the groundhog sees his shadow, that's high pressure, and that it's going to be cold, clear and cold. So that seems to suggest there'll be 6 more weeks of winter. I don't think these folks in this picture are taking this all too seriously, but there is this is some learned fellows asking the question of this groundhog, what is and making a proclamation about what the future holds. But like that, I think even if this is apocryphal, it seems the right thing to be doing. And as we saw in the last example, there seems to be a history of using animals to predict what is going to happen with our climate, or weather or climate. And so we should ask that question. We can look at photometry and whether it's consistent, at least. So I doubt that this is although it might have some logic to it, I doubt that this is a good predictor. But at least we should ask the question. And so I'm actually going to jump right to the punchline, and the answer is yes. So atmospheric transparency is well studied, well monitored. Our atmospheric physics community need to know this answer, right? This is how you figure out what is happening to the atmosphere. You need to understand the forcing of the transparency and cloud in order to figure out what's the energy budget in the atmosphere. So this has been well studied. So this plot is a measure of the transmission. It's an apparent transmission measured from Mauna Loa, and this is the best record. This goes back to 1958, the geophysical year, and these are monitored every day. And you pull out from this, by measuring the solar irradiance, what fraction of those photons get through. So there's been some pretty dramatic events. Not only does it change, but there's sometimes dramatic change. Some cases, well, the 90s kind of fits in with my kind of career. I can remember that, but these go back. Maybe there's others that remember back beyond Pinatubo, of course, was a pretty dramatic event, or El Chican, maybe in the 80s, or even before that. I mean, there have been historically some very dramatic ones. Krakatoa is, of course, one we've probably heard about in the 1880s. You could have looked up at the sky and with your naked eye seen that transparency had gone down. There'd be a ring around the moon. It's quite obvious. and in the sun. So there have been major changes. And so when you take those out, you can see that there's a downward trend. So this isn't, I didn't discover this. You can look at Dutton et al., who are the folks at Mauna Loa Observatory that have studied this transparency. And when you take out those periods of known volcanic events, you're left with this trend. It's the black line that goes from all the way from the 60s to today, and that slope is not quite as steep as it seems to be if you just start from about 2000. So I've done the same thing. So I've taken those are published, and that trend, they find a downward trend of minus 0.16%. From 2000 to 2010 when they last in this paper. But you can get these data, and I've downloaded them and done my own similar analysis. So what you do, what I did is I took out each of those volcanic events. So where transmission went more than a third of a sigma below the mean, each of those months was excluded. And I think the lighter, that's the dark shading, and the lighter shading I think is a slightly less restrictive. So just to make sure that we're getting every month that the transmission is below the mean. And so when you take those out, you're left with a downward trend. And I actually found it's a little steeper. It's minus 0.17% per decade since 2000. So we already know the answer. Transmission is going down slowly. There may be, and I'm going to point out two other interesting cases. So since 2000, we were only, of course, we're really interested since 2000 because that's when Gemini first light 99 and 2000 are first light. There's two interesting things that happen. There's one. It is a volcanic event. I think it's Mount Redoubt in Alaska may be responsible in 2009. And that's a pretty significant drop. It's not quite as much as Pinatubo, but it's still 1% or so. And then also, since 2019, there also seems to be a bit more of a downturn. So anyway, there's the punchline. We sort of know the answer. Transmission is going down at about 0.2% since 2000. Now, do I have the title Global Extinction? So my interest then is this should impact the 0 point, right? You can't get rid of this. This is just part of your 0 point now. And it's hard to know the 0 point because it fluctuates with we're trying to find out what is the throughput you would get. What's the perfect throughput you would get? What is one single photon per second? What is it? That's the definition of 0 point. So we're trying to find that. And of course, that's going to be impacted by this effect. So for any instrument, to know that precision over many years is quite hard. So there's other fluctuations that are going on besides transmission and volcanoes. So things get better, right? So when you change the detectors, the throughput of the instrument goes up 20%, and it's also decaying from other things slowly at a larger rate than transmission. So 1 to 2% for each optic. Right, those are degrading. So every year the transmission is going down by 2%, and we know that that the observatory works hard and does the right things. It recoats, of course, on some time scale, and also cleans. Right, so that's improving. So you can go back to where you started and reverse that decay. But these are fluctuations that are happening over some time scale of years that are fighting against finding some smaller signal that's in the data. And otherwise, extinction is varying, of course, by this effect. So what you could try to do is get a very long imaging base set. It spans the whole sky over decades. And if you did photometry in every frame, every sufficiently bright object in every frame, with many objects per frame, you can beat down your noise and try to find this smaller signal. And you need to, in order to do that, you need to calibrate against some fixed sky catalog. That is, you need to find relative changes in photon flux if you want to do this over a long time. So you need a good stable catalog of brightnesses to measure against. And then, and also remove clouds, right? So a bigger effect than that also is clouds. And I'm going to come to that, how to deal with that. And then compare that. So my intention is to compare that with a simple model of the atmosphere and see if that matches. So we're going to ask the question is this transmission decaying at the rate that we expect from climate change? And I'll come back to that model. And that's what it means to get just the attenuation. So we want to remove the effect of clouds and find just the atmospheric part. That's the component of the 0 point that we want to find. So that's why hence the title global extinction. We want to use a global data set over the whole sky and find just the atmospheric part out of that. And so this is the simple model. So to first order, I've done this before. So I used Canada, France, Hawaii sky probe data to measure cloud fraction and transmission over several years, and how the simplest thing that you can do is just to recognize that if fluctuations go up and down the same amount roughly randomly, then a Gaussian is a good model for the variation. And so you only need to know what's the variance from that in order to pin down the underlying peak of that distribution, which is what we want to know. So you could just, that's what this equation is. So this is just saying this Z is just the air mass, right? So the simplest model is that just the pressure times the humidity is the air mass, right? So you're just looking at the number of particles in the way they get in the way of a photon coming in, and that goes up. It goes up, and you can see from data. So I went and got all the CFHT data. This is starting from 2000, but just from the weather tower. And it shouldn't be a big surprise that it also has, as we know worldwide, it has a trend. And the trend is that the temperature, the middle plot here is the temperature. Temperature is going up. There's wiggles, of course, but the trend is up. And pressure goes with the temperature, so that you can see there's wiggles, but pressure is going up. And just in line, so the bottom plot is relative humidity. Actually, this is a log plot, but it goes, right? It goes with the same trend. So humidity is relative humidity, but the number of the humidity overall is going up. And they're going up at the rate that roughly that you would expect for well-known temperature growth of the atmosphere. It's about 0.2 degrees Celsius per decade or more. Actually, I think it works out to be a little more than that, 0.5 degrees Celsius per decade. And that just grazes the humidity. And so this simple model of the air mass, right, pressure times humidity, is a good model. And actually, so what this is the model down here in terms of the different time periods. So the average model, I'm sorry, it's 0.7 degrees Celsius per decade, is what you get from this plot. And attenuation is it's a percentage, right? So it's the relative change in the air mass, the relative change in the attenuation. There's more stuff. Is 1.7 millimegs per decade, is put as a magnitude. And then the other models, there's a minimum. The minimum is the smallest slope that you could make against that. And the maximum is the extreme is the maximum that you could do if you took the minimum case, the start in 2000, and the maximum. So that's what this is in this plot to the right. This is just the first plot I showed, but the last 20 years of it. And also, I guess there's one other thing that's been added. That's this thin black line. Those are nephelometer measurements too. So aerosols that you measure at Mauna Loa are also going up at roughly the same rate. and that's just what you'd expect, right? It's just more attenuating particles in the way. So just to I think I've color coded, and as we continue on with this, that this will be color coded. The orange line is that average model at 1.7 millimegs per decade, rising the temperature 0.7 degrees Celsius per decade. And I'll point out, and the model, the extreme and minimum model cases are shown. There's also shown a baseline case. The baseline case is just 0.1 degrees Celsius per decade, which is what the temperature rise was if you look back more than 100 years. So the original the limit that we could measure starting from the Industrial Revolution it's steeper than that, and it's possibly getting steeper, right? And then we'll point out one other point is that this blue spike here, that's the 2009 incident, volcanic episode, and that we'll come back to that because that's going to help show that we can see this change. We'll look for that. So this is what you'd expect in your distribution of measurements of stars. Of course, GMOS is calibrated. There's a 0 point that's measured from standard star fields. I'll come to comparing with that, but that's what we need to do. So to measure this over a long time scale is to get a distribution of the brightness of a group of stars, of a ensemble of stars or objects. And so that's what this is. What we're going to do is this is just a model. You take that simple model. The black line is that Gaussian, right? So just the distribution of air based on that simple air mass model. And clouds are, as I showed in I pointed out from that the sky probe data, you know as a fractal. So that's what this equation is showing here is that, so the number of clouds of a certain thickness is a strong power law, and that's true for I've seen that in various places. It's been measured for Mauna Kea, but that works for also the high Arctic for clouds. There is that you have a power law, and I'm just going to stick in the values of alpha. So it's about minus 1.84, I think, is the slope of that. So thin clouds are common, right? About half the time, photometric skies is still thin cirrus, right? So they're persistent. So thin clouds are effectively almost all the time, but thick clouds are rare. And so that's how we're going to come up with how that distribution from a Gaussian has changed, what effect do clouds have. So I'll apply this simple power law model. That's what this upper gray line is that's photometric skies, right? So what changed to the black line is made by adding those fractal clouds, and that's the light gray rather. So that's the combination of the two, right? So the black line, the Gaussian plus the power law is the light gray. So you can see that what it does is effectively it shifts the Gaussian over to the right, a small amount, just about maybe 3%. And we're going to be looking for a percent level effect. So it's a small but effectively constant effect. And also what's nice is that MLO, Mauna Loa and Mauna Kea, and MLO to Serapichon happen to be roughly similar differences in pressure ratio. So we're going to stick with a constant offset. So the median attenuation, so the red dashed line, so the median of extinction is roughly the peak, right? That's what the hat means. The hat means the mode. So the mode of that Gaussian is shifted by this amount, and we're going to assume that that's effectively a single constant is what's needed. because the pressure ratio between those two sites is comparable. So a single constant should do it. And that's what you get is the orange line. So the orange line is the shift in the atmosphere that you get by this change of 1% or so. I think it's actually shown for 1% is what the shift in the atmosphere should be, not due to clouds, but due to change in the atmosphere. The effect of clouds is going to be taken out as a constant. So that's what the bottom equation is showing. So we can back out the 0 point by assuming that we correct for clouds as a constant, and that's what the offset is, and it returns the peak of the atmosphere. So it returns the attenuation to the air only. That's what A hat is. And so what could get us? What could go wrong? And that is that you need to have sufficient data that you can beat down the random noise in order to get that peak. And I didn't make a very sophisticated model of GMOS, but thanks to Andy, I asked for the dates of when all the changes occurred. So remember, I talked about what variation happens in the throughput of the instrument, which is what you're measuring against to get the 0 point. And the dates are known, right? So you know when recodings are made, and that's what's shown in the bottom right is a simple model of the 0 point changes because the photon flux goes down as the coatings decay, each one, M1, M2, and the tertiary, as those go down roughly 1 to 2% per year. That goes down. That's why the line goes up. And then at times you change in a new detector, and that's a more abrupt one. I look for one in this plot. There's changing from the E2Vs to Hamamatsus, that's here off to the right. Then the line goes up. And of course, there are already calibrations of this 0 point measurements calibrations are made, and that's what the red dots are. Is those are the available 0 points from standard star fields, and then that's the difference is shown in the bottom plot against the simple model, which is that orange line. And the dark and light gray points are my model based on this simple-minded decay and improvement based on new detectors and cleaning. And cleanings are the difference between light gray and dark gray, assuming 1 cleaning per year or 2 cleanings per year. The point is that this model is already sufficiently good to get the 0 point to reproduce the known calibration of the 0 point to within a few percent per year, right? So you need to beat down the variation per time. So per year, you need to have sufficient samples that you can get the error to within 1%. That's the kind of level of measurement that we're trying to make is over the course of many years, can you measure a % effect? So within a year, you need to get 1%. So what it says is that the current calibration, it's more like about a 5% fluctuation year to year. And so to get down to 1%, you just need more. So it's saying that you need roughly 1,000 frames per year if you really wanted to get the fluctuation per year, the sampling, the precision per year to within 1%. And so that's the goal. And GMOS can provide that, of course. So GMOS is the most popular instrument, and it's imaging often, almost every night. Of course, in the standard Sloan filters, G, R, I, and Z, rarely U. And it's a pretty good size field of view. It's 5 by 5 arc minutes. So in every 5 by 5 arc minute field, there's roughly about 10 or so Gaia objects to calibrate against. So you can take calibration fields, and you need to do that to be consistent with other analysis. But that was the question I asked: is can I do that? Can I just go and get images and calibrate against Gaia, and which filter, of course. And so that's what's shown in the upper, just to close the loop on that, why that was picked. So R band, this is the Sloan R band for both north and south, and G, the white line, is Gaia. And so R band happens to be smack dab in the middle of G, and that's most of the data. So about half of the imaging with GMOS is in R band Sloan, and so that should be calibratable against the Gaia G catalog. Of course, Sloan is a northern survey, not a southern survey, although Gaia is all sky. So we'll come back to intercomparing those, and that's what motivated this whole study, is that I just thought I'd be bloody minded and say, well, I'll just go to the archive and get every GMOS R-band frame I can get. There's tens of thousands of those, and that seems an arduous task, I think, logically. But it was COVID times, and I had and working at home, I could come up with a way to do that. And the only way I could come up with a way to do that is because of the nice work of Kathleen et al. And that's because of dragons. So I used dragons to process each frame. I did it in chunks. I couldn't do it all at once. So I did it in, I think, chunks of time and exposure time, drawing it from the archive. And then just processed each of those frames and did photometry, I think a 4 arc second aperture on every object within the frame. And each of those looking in the catalog and finding the Gaia magnitude. And that actually is pretty good, because you've got, it's fairly uniform, and it's quite deep. So like I said, there's 10 to 20 objects in every minute or so GMOS frame. And I just not making any selection other than saying these are in the archive and publicly available. There's no selection based. It's just science images, right? So these could be pre-imaging for making a slip mask, or they could be direct science images. I don't make any selection based on that. And this is a distribution of those brightnesses. On the right hand side, the R is the Sloan R magnitude for those that are the habit, and the white is the Gaia catalog of all those samples, and the black line is the combination. But anyway, you can see the black line is the peak of that. It's about 19th magnitude, and it's good down to maybe 20th, and complete. So that's actually quite useful. It's a uniform combined data set for both telescopes. So this is showing also, of course, Pachon. And like I said, although it's 30 degrees south, of course, that is uniform and identical, a twin to the north. I thought was the right way to say this, is that this is a global data set compared against Gaia. And here's the results. So I took every frame from 2003. I think there was some that I think after 2005, I think was the only ones I could really take, because there was some missing information, like the meteorology in the frames before then. And you can see that it didn't. There's no, this is every position. There's no control over this. This is every position on the sky. And over 20 years, I mean, GMOS has looked at every possible orientation between the two in every season. Along the right-hand side is, we'll come back to object width as well. So it's just, there's a measure of the width within that 4 arcsecond aperture. The middle one is the object brightness with air mass, and the relative, and the bottom is, of course, the difference in measurement from the catalog, so giving you extinction. Was there any variation with moon phase or sky, moon phase or angle or sun angle? Doesn't seem so. The dashed line is the median for each of those. Going back over to the left-hand corner, so there does seem to be an effect with image quality, so with the size of the images, and that's not too surprising, right? And so it's you'd expect the image quality to get better as with lower air mass. And so the dashed line, the solid line is just a linear fit. The red dashed is the median, and the white line is a quadratic fit. So what you might expect is that as things as seeing improves, that you're going to get a better photometry, and that's not too surprising. I think it's just something to remind us that, or remind us in an analysis, is that we should look at the best data, right? So you should expect that there will be a bias that the poorer data, poorer seeing will be noisier and also may have higher extinction, at a higher air mass and higher extinction. So we will look at the best data, so the best possible measurement that you get the lowest attenuation and the closest to the true 0 point. And the upper left is just a plot of what you'd expect is versus the catalog. So the catalog is the truth, the outside the atmosphere truth, and also Sloan R. So Sloan is shown in the red dots. I think south data have a black dot on top of them, and the dark gray are the Gaia sample, so the Gaia catalog value versus the measured value in each frame. And that's what we're going to look for, right? We're going to look for whether this one-to-one line shifts downwards in time. So total of 1 million observations, and then there's pruning to that based on how much whether there's cloud or not. But there's no so if attenuation was more than half a magnitude, those are going to get thrown out. But this is a plot of the observer's sky clarity. So the fraction of all those observations which are retained, which were photometric, right? So what fraction of those should really be clear? What you don't want to see is some trend, right? So this could be spoiled if it's just getting cloudier, and that doesn't seem to be the case. So this is since 2005. This is the average. The blue line is the average, both north and south together, of the clear sky fraction, photometric fraction per year. The whiskers, I think, are north versus south. So whether there was you might like look for an El Nino year. Is there some year that's cloudier than others? And doesn't seem to be. There doesn't seem to be a trend of maybe this year was a little worse than usual. And that's what's shown on the bottom in the table, right? So this is what the output of the photometry. Typically, there was always more than, I think, 5,000 samples per year per telescope. Typically about 10,000 samples. And that's what we wanted to get. We were expecting that we needed about 1,000 samples to beat the noise down to a % level per year. And over both telescopes, overall time was probably about a third to a bit more than a third of the total data set. And this is broken down a little bit more. So the far right hand columns are the photometric fraction. As you can see, that doesn't really change much, and over all the data set, about 80% of it is both photometric and with data. And the best fraction, so coming back to, I promised to say that we'll look at seeing as well. So the best fraction is both photometric and best seeing, so also IQ 50. So it's the absolute best part of the data set. And the total of that is something like, I think it's 17,000 frames, and with each about 10 to 20 samples per frame. So just cranking through on my little laptop on my desk. I think it took maybe a couple months to process all of those data through. I guess I was bored. So what's the answer? What are the results? So we get the left-hand plot is just what, remember when I showed the model of what I expected to see. So that's the distribution of attenuation for each of those frames. And you can see that so Gaia G is the distribution of the total, right? And you subtract that offset from there to correct for cloud. So that's what this, just again, like the model showed, you just subtract a constant in order to get the peak of the air itself, just the air that was in that measurement of attenuation. And that's the black for the total. And then the orange is actually the period, which was shown to the right, is that period in 2009 for an event in the first half of the year. So going over to this plot on the right, that's just showing that worst period. And you can see that, and this black line here with the blue shaded up to it is the MLO transparency. The dark symbols with the error bars are the overall attenuation for all the data that was available, and the white dot is just the best data. So those seem to have, it's not, it's not very much of it, but it's just enough to see that yes, it goes up during that month. And it happened that there weren't any calibration observations in this time period. So that the only way to get this measurement was by taking every single frame that happened to be taken. There wasn't calibration in R for this period. So that's why you could see it. And the dashed red line is the median, overall median of the extinction, and the black dotted is just for Sloan R, right? So the white here, just to pull it all together, the white here is what you get for Gaia, right? So looking at what is the difference from the outside the atmosphere measurement of what the brightness should be compared to what you get, and you can see that the Gaia overall, this whatever object happened to be in the frame, they are about 1% or so worse than, fainter than they should be. So those photons went somewhere, and that's the Gaia, and that's shown again over here in a distribution on the right. So what it says is that the 0 point, the attenuation got pushed to the right in this plot of occurrences, right, and the distribution. So the distribution changed, and it changed in the worst period by about 1% or 2. But that's roughly what we're going to expect to see. We're roughly going to expect to see a shift in the distribution of the attenuation of about 1% or 2 over the course of 20 years. And so that's, and I show the model here just to verify. I'll toggle back and forth a couple times. So you can see here's the expected shift in the orange. That's the part, the shift that you see in 2009. That's about 1% or so, and that's what the model said was going to happen. So there, yeah, it does what you expect. And then here's the final plot over the 20 years. What do we see? Starting from the top. So the 0 point is just remember, this isn't an input, this is an output, right? This is what the 0 point that you get by measuring the difference in the expected truth outside the atmosphere versus what you actually measure in terms of brightness. And so the red are the Sloan values. Remember, they're not in every frame, and they're certainly not in every frame from the south. So I think the black dots are cases when Sloan objects are in the frames for the south. And then the gray are Gaia, which is every frame available. And then the next plot is just going back to what I started from the beginning. So object width, do we see any change in that? The blue line is the average of both north and south. I think doesn't seem to be a measurable trend. If anything, it's maybe getting better, but that's the black line is a linear least squares fit to those data. Although one might notice that the excursions from that are larger in the last 5 years. So the five worst months averaged in a month have all occurred in the last 5 years in this data. But doesn't seem to be a trend to getting worse for object width. But pressure, exactly like you expected, pressure is going up. Blue line is the average for both sites together. I think there's a thin black line and a thicker gray line to show the difference between north and south. Temperature going up, just like you expect, and relative humidity going up, just like you expect. And actually, if you plug those numbers back into the original model, I think you get 2.22 millimegs per degree Celsius if you use these data. Remember, these are meteorology that comes from the frame itself. So these are the Gemini measured temperature, pressure, and humidity that you get during that observation. Remember, the CFHT data were just all data together, a continuous data. This is dome closed. This is when the observations are made, so not biased. But you get the same number. 2.22 versus 2.339 millimegs per decade is the number that you get for these data. And then the bottom is the answer, right? So the dashed red line is the median extinction over the whole data set, measured from the Sloan data points. And then the white is the offset by the offset is the Gaia median extinction, right? So you can see it's pretty smooth, and it's going up, and it's going up in the same rate, and so that's repeated. So each of the yearly values is plotted along the bottom. And the white dots are the best data, and you can see those white dots year by year are going up a little bit each time, and they're actually going up roughly in accordance with the orange line, which was the mean model that we started from in the beginning. And that's using the data, the numbers for temperature, pressure, and humidity that you get from the Gemini data. So they're going up at that rate of 2 millimegs per decade. And what does 2 millimegs mean? That's what's on the table to the left. The table is let's see, put both together from 2005 to 2021. Best together says that this is the initial attenuation that you'd have, and then the slope is 2.7 millimegs per decade for that. And I think that corresponds to roughly 0.7 degrees Celsius per decade is the change. That's more than the expected global change in temperature over 20 years, which is closer to 0.2 degrees Celsius. So it actually seems a little steeper than you expect for global warming. But that's the conclusion. So the conclusion is that yes, throughput is going down. You know, Wyerton Willie, Puxatani Phil, they were right. It is going to be a short winter. I guess this would be the answer they gave. Is that the attenuation is going up as you expected, and maybe just some other comments about that is that to get the calibration to see something like the event in 2009, you actually need calibrations more like weekly than monthly. So that's maybe also useful. But the attenuation in the optical and R band is going up at the rate of global warming, in fact, a little bit more. And that's, we should take that to heart, because although that seems pretty small, 2 millimegs is a pretty small amount, even per decade, but that's adding up, right? So what is 2 millimegs per decade? Well, that's kind of like a 12 centimeter aperture, taken out of the primary out of your throughput every year. And that's not just Gemini. I mean, it's not like it's the Gemini problem. It's both Gemini north and south. It's every other telescope too, in proportion to the aperture, right? So it seems to be we should watch out for that, and certainly that it should be part of our analysis of photometry, is that we're losing a little bit of throughput all the time. So that's going to be true for Rubin. That's going to be true for other observatories down the road. Is that we should watch out for that. Global warming is going to affect photometry too. Thank you.
Thank you, Eric. Is there any question? Yes.
Nice talk, Eric. So climate changes are making some places wetter. It's more wet, it's more humidity, but other places are getting drier. Does that mean that photometry in those places is getting better?
I see what you mean. So this is, I don't know, but this is an active field of research, and I did not delve into other research that's going on about predicting based on sort of like MM5 models of what you could expect variation over the Earth. I'm only using, that's true, I'm kind of cherry picking. I'm picking two excellent sites, some of the world's best sites, and taking data from those. So I can only say that the meteorology from Mauna Kea and Anamalo and Pachon, that humidity is going up. But you are correct that could mean that if a site is becoming drier, that this model would be, would not necessarily apply. But I do know that people are looking at variation. For example, what difference could it make in other parts of Chile? That's an active field of research, and I think if I could give a sort of a picture of it, I think the answer could be simply that there's more variation. Right? So as there's larger fluctuations in humidity, maybe some places are getting drier, but in general, as fluctuations get larger, that your excursions from the mean go up. So all places could possibly. What I'm saying is that all places could possibly get worse because the excursions get larger as changes are growing. Right? Thanks.
Clara?
Hi, Eric. I have a question regarding the data, how you process the data. So you said you were using dragons. How did you get the photometry from it? Is like directly the data table that dragons provides you, or because you said you were using aperture photometry, right? Yes.
Sorry, I may not have mentioned it, but I use dragons to process the frames. That's simple processing, DC offset, flat fielding. And then once processed, I wrote an IDL code. So it's a proprietary. It's my own photometry code. It's very simple aperture photometry, 4 arcsecond aperture and a 2 arcsecond background subtraction. That is effectively AO aperture photometry. I didn't investigate more sophisticated photometry, fitting photometry. But I think I did look at sizes of objects within the frames, so measuring the widths and looking for things like trails, right? So non-sidereal tracking and throwing those things up. So I did some vetting in terms of that kind of problem. But aperture photometry at 4 arcseconds was very effective. I didn't have any problems as long as it was the best, the good quality data is particularly good. But that was an IDL code of my own. I do plan to put that up. I can make that available. I've looked at, I've talked to CADC about possibly putting that someplace available, but that was my own code, not part of Dragons.
Thank you.
We have 2 online. Michael, you want to speak up?
Yeah, hi, Mike Liu here. I had a random question. You showed the photometric fractions for both Gemini North and Gemini South over various years. I was wondering, are those correlated, or are the two sites their photometric performance independent from year to year?
That's a good question. I don't know. I think there are years where there's larger variation than others, and they may be like El Nino years, for example. Right? So I don't know the answer, but I didn't really look at correlations between the two. But in the average, it's not getting worse. And but there is some years with more variation than others, but I didn't look at it beyond that.
Okay, we reached the hour, so we can thank Eric again. And hopefully
Thank you.
Thank you.
Thank you.